What up, peeps? Welcome back. Today we're going to be talking about Med Calc. Yup. Don't get so excited. But if you guys going through your training and going through school, this is a pretty important topic. If you're listening and you've been on the field a while, or maybe you're a bit seasoned, then this might be a little boring for you, but it'll be a good refresher, right? This is not to replace an official didactic lecture in Med Calc. This is to kind of supplement and try to help you guys review it or go back and try to get your skills back up in doing some of these Med Calcs that you might not see on a daily basis. But one of the first concepts we got to get down is actual converting pounds, kilograms, and kilograms to pounds. I don't know about whatever your institution does. The institution I teach at, they're not allowed to use calculators, so we got to do everything longhand. So whenever we're doing mainly drips, but also some boluses or weight-based, and we have to do our best to try to calculate patients' weight. And I suck at that, so paramedics generally tend to inherently guess to the nearest tenth. So your patient might be 80 kilograms or 90 kilograms or 100 kilograms, whatever makes the math easier for you. Because, I mean, let's face it, if we're given 125 milligrams of succinylcholine, it's not going to make too big of a difference if we give 130 because we guessed the patient's weight wrong. So, but we have to learn how to do it longhand, especially for our tests that we're going to see in paramedic school and for written exams. So we have pounds that we have to convert to kilograms. And on your test, you'll see it written as, say, the classic 176 pounds equals how many kilograms. Well, the easiest way to do this would be to take your pounds, and what you're going to go ahead and do is divide that by 2.2. So you're going to have 2.2 divided by 176. Now, I know we're in paramedic school, we're not mathematicians, but we got to remember that if we're doing this, if we're dividing a decimal, the easiest thing to do would be to move that decimal over and make it 22, and move this decimal over to make it 1,760. And we know that 22 goes into 17 about 8 times. That'd make it 176 because you times 8 by 22. 0, you bring down your 0 there. 22 goes into 0 times, so that is your classic 80 kilogram patient. Right? Or you can do the classic, what they call it, quote, 3 a.m. way. And that's by taking half of your patient's weight in pounds and then subtracting that by 10%. And that'll give you a quick down and dirty weight. But, I'm not going to get into the philosophical debate here on why are we calculating pounds to kilograms, an actual unit of mass being kilograms and a unit of waste efforted by gravity in pounds. That'll be for another lecture. But that is the first concept we got to get down. So converting pounds to kilograms, we're taking the patient's weight and we are dividing it by 2.2. Now, on your test as well, you might see a question written like 80 kilograms equals how many pounds? And in that case, we just do the opposite. We take our kilograms and we times that by 2.2. And we get 2, that would be 16. That would be 0, be another 16. Don't forget our decimal. 0, 6, 7, 1. Drop our decimal. So our answer would be 176 pounds. All right. So that's the first concept we got to get down. All right. The second concept we got to kind of get down is our units. All right. So we're going to have a unit that we worry about in, we'll say, mass. All right. So we work with micrograms, which is written a couple different ways. It's got this Greek symbol here that looks like a U and then a G. That's my G. You can also write it MCG, which is not the JCO approved way. Or you can also write it with that little U Greek symbol CG. That's micrograms. All right. That's the smallest unit that we really work with in med math. Then on top of that, we have milligrams, represented as mg. And then on top of that, we have grams. That would be our mass. And we also worry about volume. All right. Now, unlike mass, we don't really worry about microliters. What we are going to worry about is milliliters as the smallest unit, and then liters as our bigger unit. Now, these are all kind of nice because they go up in 1,000. So we can say that there are 1,000 excuse me, 1,000 micrograms in 1 milligram. All right? There's 1,000 micrograms in 1 milligram. And on top of that, there's 1,000 milligrams in 1 gram. So they go up in units of 1,000. The same thing with our milliliters. There are 1,000 milliliters in 1 liter, which makes the math kind of nice for us. Because on your exam, or on tests you take, you're going to get questions like this. It's going to say 1 milligram equals how many micrograms. All right. Now, just for the sake of showing you, I'm going to write big with an arrow and small. Big to small. Meaning that if you're going from a bigger unit of measurement, milligrams, remember there's 1,000 micrograms in 1 milligram. So if I'm going from a bigger to smaller unit, all we're moving is our decimal spot 3 times. All right. So I'm going to write 1 here. And my decimal in 1 is right there. So I'm going from 1 milligram to micrograms. So I'm going to move my decimal spot over 3 times. So I'm going to put some more zeros this way and go 1, 2, 3. So now I have a unit of 1,000 micrograms. So 1 milligram equals 1,000 micrograms. And that's from big to small. Remember, if we're going from a bigger unit, which is milligrams in this case, to a smaller unit, which is micrograms in this case, I'm moving my decimal place over to the right. Now, if I'm going the other way, again, I'm going to write big, small, and with another arrow this way here. All right. Now I get the question, 1 microgram equals how many milligrams? Well, now I'm going from a unit that's smaller, micrograms, to a unit that's bigger, milligrams. So I'm going to be going to the left. So here's my decimal, but I'm going to be going this way. So I'm going to draw my zeros this way. And I'm going from small to big, which is from right to left. So I go 1, 2, 3. So my answer would be 0.001. All right. This is extremely important in med math because we have to convert units all the time in order for us to get the right answer and the right doses. So if you're converting a unit that's from a size bigger, which is milligrams, to a smaller unit, micrograms, we are moving the decimal 3 places to the right. If I'm going from a unit of smaller, in this case micrograms, to milligrams, I'm going from small to big, I am moving my decimals from 3 places from the right to the left. All right. Pretty easy so far, huh? All right. Now we have to worry about components or variables within the equation. And there's a couple things that we got to understand and a couple of terms that we got to throw out there so everybody's on the same page, all right? So when I'm looking at my mathematical equation and I'm reading my problem, and I'll show you, we'll do problems a little bit later here. But within the problem, we're going to have a couple of things. We're going to have our desired dose, all right? And that is DD. We're going to have our dose on hand, or we can abbreviate that as DOH. And we also have our volume on hand, which we can abbreviate as VOH. Then we also talk about GTTS per minute. And all that stands for is drops per minute. GTTS comes from the Latin gutta, which means drops. So this is a Latin-derived word, drops per minute. And there's a couple of things that we worry about, right? You got to keep in mind. We have a saline bag here. Ooh, bag of saline, all right? Normal saline. And connected to this bag is an IV set that goes into the patient's arm. All right. I'm not an artist. All right. Well, this drip set here is capable of doing a couple things. This can either be a 60 drop per minute set. It'd be a 10 drop per minute set. Now, there's also 15s, but for the sake of everything, we're going to talk about 60s and 10s. All right. So if I have a 60 drop per minute set, I can call that a micro set. If I have a 10 drop per minute set, I can call that a macro set. All right. Macro, big drops. All right. Micro, small drops. So I have a 60 or a 10 drop per minute set, or a 60 drop set as the lingo goes, or a 10 drop set as the lingo goes. But that doesn't mean that this drip set is capable of dripping 60 drops per minute, and that's it. If I open this drip chamber wide open, it's just going to dump fluid out. We can't even count the drops per minute. What this means, what this drip set means, is that every time 60 drops comes out, it equals 1 milliliter. That's what a 60 drop per minute set means. It means that every time 60 drops comes out, I'm giving my patient 1 milliliter. A 10 drop set is the same thing, except every time I give 10 drops, I give 1 milliliter. So I give less drops for the same volume. That's why it's called macro. It's a bigger set. We generally use 60 drop sets for medications that we have to titrate, that we have to infuse and watch carefully. We usually give the 10 drop sets when we have to give fluid challenges or fluid boluses. And there's a couple instances where we can do it to make our math a little bit easier. But, we're not here to make it easy. We're here to actually do it right for our patient. So we're going to start with our desired dose. The desired dose would be how much medication, or volume for that matter, that you want to give your patient. So if the dose of lidocaine, we'll say for a drip, is 1 to 4 milligrams a minute, all right, and the equation says that you want to hang a lidocaine drip at 2 milligrams a minute, well, that would be your desired dose. Your desired dose in your word problem is going to be said like, the doctor orders you to give 2 milligrams per minute, or your protocol says to give 2 milligrams a minute, or you are to give 2 milligrams a minute. Whatever drug you want to put into this patient's arm is your desired dose. Your dose on hand is how much drug you actually have. So if we want to take that number again and say the doctor ordered you to give 2 milligrams per minute of lidocaine, you have 1 gram in 250 mLs. All right. Well, that's what you have. You want to give 2, but you have 1 gram. This 1 gram is your dose on hand. This 250 is your volume on hand. That's how much volume you have on you that you are able to give your patient. All right. Which is going to bring me into my next concept when we're talking about concentrations. All right. So I'm going to erase that. And I'm going to get my 1 gram in 250 milliliters. All right. Another important concept to get down is, I'm going to write desired dose again. Desired dose and dose on hand. All right. These are the two we're worried about right now. We always want to convert our dose on hand to our desired dose. Never the other way around. Never the other way around. All right. Whatever my desired dose wants to be, or it should be, then I need to convert my dose on hand to that. And we'll notice that my math problem said that I need to give 2 milligrams per minute. That unit is milligrams. I have drug, but I have it in grams. So I have to convert grams to milligrams. I have to convert my dose on hand to my desired dose. And we did that before. Milligrams is smaller than grams, so I know I'm going to have to move my decimal spot to the left, all right? So how many milligrams are in 1 gram? Well, that would be 1,000, all right? We have 1,000 milligrams in a 250 milliliter bag. Now, if my math problem says to find the concentration of this mixture, all right, if it says to find the concentration of this mixture, what I want to do is make my denominator 1. That's my goal. I need to divide the numerator and the denominator. This bottom number from the top, and that's easy. 250 goes into 1,000 4 times, right? So that would leave me with 4 milligrams per 1 milliliter. That's my concentration. I have 4 milligrams per every 1 ml. So if your math problem asks you to find the concentration of it, that's what you're doing. You're trying to put this bottom number to equal 1, divide these two numbers into each other, and you get 4 over 1. That is your concentration, okay? We have to do that in order to use the mathematical equation that I'm about to throw at you here in a second, all right? So, there are many different ways to calculate your drips and to calculate your drugs. Classically, there's the master formula way and there's the 3 equation way. What I'm going to show you today is the master formula way, right? Which would be desired dose times weight times solution set over concentration times time. Now, it would behoove you to memorize that. Desired dose times weight times solution set over concentration times time. I don't know why, but I remembered it by saying, Dunkin' Donuts will taunt sloppy sheriffs, can't they? It always stuck. All right, it always stuck. So using our problem before, all right, we said that we wanted to give 2 milligrams per minute of lidocaine. It said we want to use a 60 drop set. All right, and it comes packaged 1 gram in 250 mLs. That's all the information I need. Now, looking just at my equation here, I have my desired dose. Well, what out of these numbers is my desired dose? 2 milligrams a minute. That would be my desired dose. All right. My weight. Well, this drug isn't weight-based. It would be weight-based if it said I needed to give 2 milligrams per kilogram of body weight. Well, that's not the case in this situation, so I don't need weight. So I can just cross that out. I know I'm using a 60 drop set. All right. So I put 60 drop set here. Now it comes to concentration. Now remember, before we plug our numbers in, we got to convert our dose on hand to my desired dose. Meaning, my desired dose is in milligrams. My dose on hand is in grams. So I need to convert that to 1,000 milligrams over 250. 250 goes into 1,000 4 times. So I have 4 milligrams per 1 ml. So that is now my concentration. 4 milligrams in 1 milliliter. Now I'm going to be giving this every minute. I need to give 2 milligrams a minute. So my time now becomes 1. And then we just simply do the math. All right? 2 times 60 is 120 over 4. All right? So what's 120 divided by 4? Well, let's see here. 4 goes in 3, 12, 0, 0, 30. Well, guess what? That's my answer. 30 drops per minute. Now, at the end of this podcast, I'm going to show you how a way where you can figure this out in about 5 seconds. But for right now, we need to get the concept down. All right? Remember this equation. Desired dose times weight times solution set all over your concentration and your time. And we're going to do plenty of practice of this. All right? But this is the master formula way. We're going to see it a whole bunch of times. All right, but there might be some times where, or there will be some times actually, where you have to give a bolus, a bolus drug, all right? That example we just did was a drip. Well, this is a bolus, and bolus is just a set amount of volume at one time, all right? So we're going to say that we got to give atropine, all right? And I'll give you an easy example, because Because like I said, this podcast is just for you to kind of get the concepts down, but you're going to have to sit down and practice this, all right, over and over again until it becomes like second nature. But we got to give atropine. And we need to give atropine 0.5 milligrams IV push, all right? And the equation says that, or the word problem says that atropine comes packaged 1 milligram in 10 mLs. Now, just from sheer common sense, we can figure out that, if we got to give 0.5 milligrams and it comes 1 milligrams in 10 ml, then all I have to do is push 5 and I got my dose. But we're going to use our equation here as an example, because if they're not as easy as that, we can always go back to this equation here and it'll always give us the answer. So we have desired dose times weight times solution set over concentration times time. So out of all this, we already said that we need to give 0.5 milligrams IV push. Well, 0.5 milligrams would be what in this equation? It would be my desired dose, 0.5. Do I need weight? No. This drug is not weight-based, all right, so we can get rid of weight. Do I need a solution set? This isn't a drip, all right? This is an IV push, so I don't need solution set. What's my concentration? Well, going back to this, remember? We got to give 0.5 milligrams, and I have 1 milligram per 10 mLs. The first thing I need to think about is, do I need to convert my dose on hand to my desired dose? No, they're the same unit, all right? So how do I make this bottom number 1? Well, just like anything else, I need to divide 10 into 1, all right? So, just to kind of show you, you can't divide 10 into 1, so we move our decimal over, and that's 1, all right? So we're going to have 0.1 milligrams per 1 ml. I'm sorry, 1 ml, all right? That's my concentration, so 0.1. And when I divide, I'm sorry, I'm going a little bit too quick, and we don't need time. We don't need time. It's straight bolus. So which leaves me with my equation as 0.5 milligrams divided by 0.1. And if I divide these two numbers out, it comes out to 0.5 milligrams. All right? Because that's right, there's milligrams as well. So that's 0.5. And you can do every single bolus med math problem like that as well. Right? So when you're doing your med math, you're going to have bolus questions. You're going to have drip questions, which we did with the lidocaine, and we did bolus with the atropine. We're also going to have volume type questions, all right, in which they're going to say you need to give 2 grams of magnesium sulfate over 10 minutes per se. All right. Now, in the field, all you know is that you need to give 2 grams of mag over 10 minutes. In your mathematical problem in school, you're going to have everything written out for you. You're going to have 2 grams. You need to give 2 grams over 10 minutes. You have a vial that's 2 grams in 10 mLs. And you have a 500 ml bag. All right? Now, I don't want to worry about that right now because I want to show you the actual concept of it. So if I need to give 2 grams of mag over 10 minutes, well, this poses a different problem, all right? It's not a bolus, as in I need to give 2 milligrams IV push. There's no time involved there. It's not a drip saying I need to give 2 milligrams every minute, all right? It's not that either. We have a set amount of minutes that we have to give it. Well, I'm going to give you 2 different ways to do it. We're going to use my favorite way, the volume way. Now, if you wanted to mix this bag yourself, you got to remember that you got to give this drug, you got to give 2 grams over 10 minutes. And we want to give drug. We don't necessarily want to give volume. So you look at the size bags you have. You got a 50 ml bag. We got a 250 ml bag. Let's see what else we got in the truck. 50 ml bags. And we have 1,000 ml bags. Well, if I put 2 grams in 1,000 milliliters, it means I got to drip in 1,000 milliliters over 10 minutes. Not very practical. We don't want to kill our patient. If I use my 500 bag, I got to give 500 mLs over 10 minutes in order to give that 2 grams if I put that in there. I don't want to do that either. 250, Might not want to do that either. Let's make it real easy and put 2 grams in a 50 bag, in a 50 ml bag, all right? So if I put this 2 grams in that 50 ml bag, then this number really doesn't matter anymore, because I know that I got to give this 50 mLs over 10 minutes in order to give 2 grams. So all I need to do in this case, I got my 50 mLs and I times it by my solution set, or I'm sorry, my solution set over my time in minutes. And if I use a 10 drop set, those just cancel out, and my drip rate is 50 drops per minute. So whenever I have a problem that's telling me to give drug over a certain amount of time, the easiest way to do it is just take your volume on hand, times it by your drip set, and put it over your time in minutes. That's your problem, all right? So we can do volume on hand times our solution set over time, all right? Well, let's go back to the master formula, see if that works. All right, over concentration and time. We said we need to give 2 grams over 10 minutes. Well, in this case, remember we're putting 2 grams in a 50 ml bag. So that becomes my desired dose. Because in order to give this 2 grams, I need to give that 50 mLs. So we'll put that in the equation. We don't need weight. Here's my solution set. We're using a 10 drop set. My concentration, I don't need that because there's nothing concentrated. And my time is 10. So just like we did before, the 10s cancel out, which leaves me 50 mLs and drops. So I have drops per minute. That's simple. Now we're going to do the dreaded dopamine question. Now, schools love giving dopamine problems because dopamine, as medics, is one of the only drips that we do that is also weight-based. So here's your classic dopamine question. You're going to get a question that says, you are to give dopamine at 5 micrograms per kilogram per minute. Your patient weighs 80 kilograms. You have 400 milligrams in 250 mLs. What is your drip rate? That's what we need. Using a 60 drop set. All right. Now don't let this problem freak you out. You already know what your desired dose is. It's 5 mics per kilogram per minute. So remember, just while you're studying this, just kind of write all your variables to the side. All right. So right to the side here, I have my desired dose, dose on hand, volume on hand, and solution set. Well, the thing that kind of confuses you at first is that you need to give 5 mics per kilogram per minute. It throws in an extra component here, weight. It tells you that your patient weighs 80 kilograms. Now, the math equation might throw in another thing and give your patient's weight in pounds, in which you have to convert pounds to kilograms. So we're going to say that we already converted it. It's 80 kilograms. Magic number, and we'll find out why here in a second. So if I got to give 5 mics per kilogram per minute, I just take my 5, times it by my weight. 5 times 80 equals 400 mics per minute. That now becomes my desired dose, 400 mics a minute. My dose on hand is 400 milligrams right here in 250 mL. So my volume on hand now is 250 mLs. But wait, hope you caught it. My dose on hand is in milligrams. My desired dose is in mics. So I need to convert my dose on hand to my desired dose. So which means I need to convert 400 milligrams to micrograms. All right? Which means I got to move this decimal spot here over 3 places to the right. So 1, 2, 3. Which gives me 400,000 micrograms. That's my dose on hand. All right? So my dose on hand is 400,000 micrograms. Again, don't let this freak you out. Now, I have 400,000 micrograms in 250 milliliters. If I were to find my concentration, and if the equation says find your concentration, then all you're going to do is, divide 400,000 by 250, and that's going to give you this magic dopamine number, 1,600 micrograms per ml. So if I were to divide that into there, I would get 1,600. Memorize that number. All right, it's going to be the same every time. Now, there might be variations of the problem that we'll go over here in a minute, but that is my concentration. I have 1,600 mics per ml. So my new dose on hand would be 1,600 mics. And that's my volume on hand. All right, so that's the magic. Those are the magic numbers. All right, so I'm going to do a new screen here to try to consolidate everything. So I know my desired dose. My desired dose is 400 mics. My dose on hand, 1,600 mics. And my volume on hand would be my 250 mLs. So let's go back to my master formula. Desired dose times weight times solution set, all over concentration and time. Well, here's my desired dose, 400 mics. I don't need weight because I already calculated my weight. If you didn't do it, you can plug in 80 here and just do your math. But we already did that, so we can just times it by my solution set. All right. Remember, my original dose, or my desired dose, is 400 mics a minute. So right here is time. So down here, let's see what happens with what numbers I plug in. All right. This is my dose on hand. I've already concentrated it out. So I have 1,600 mics in 1 ml. So if I do the math here, I got 2,400 over 1,600. Now we just got to do the division. All right. 1,600 divided by 2,400. Or I could just take my zeros out. It makes my division a lot easier. All right. That'll go in 1 times 6, 8. That drops down. Wait a minute, guys. Did that wrong. Remember, 400 times 60 is 24,000. I left out a 0. So 400 times 60 is 24,000 over 1,600. All right. So now I divide 24,000 into, 1,600 into 24,000. All right. Again, you can take your zeros off to try to make the math easier for you, and you'll find that 16 goes into 240 15 times. So your drip set is set to 15 drops per minute. All right. That's your classic dopamine problem. And I'm going to show you something here. All right. This is called the clock method. And again, this is just for a review, get you guys kind of introduced into Med Calc to help you out. But this would be the 3 a.m. way to figure these problems out. Remember, if I got a dopamine problem. Now, dopamine comes prepackaged already in the bag at 400 milligrams in 250 mLs. And just from sheer memorization, you will know that that equals 1,600 mics per ml. Memorize it. Okay, memorize that. Because they might throw you some curveballs. They might say that you have 400 milligrams in 500 mLs. But don't let that freak you out, all right? You have the same amount of drug in twice the volume. So would you say that that's concentrated or diluted? All right? What would you say? Well, that would be diluted because you have the same amount of drug in double the fluid. And if that were the case, if you have still 400 milligrams in 500 mLs, then you would dilute that down by half, and you would have 800 mics per 1 ml. Just like if they said, let's see, you have 800 milligrams in a 250 ml bag. Why you would have that, I have no idea. But that wouldn't be diluted. All right? That would not be diluted. Or it would be concentrated because you're doubling your drug. Normally, we have 400 milligrams in a 250 bag, giving us 1,600 mics per ml. Here, we have 800 milligrams in the same amount of fluid. So we would have double. We would have 3,200 mics per ml, and that would be our concentration. All right? So going back to clock method. Now, the clock method, what you're going to do is in your brain or on your paper, you're going to draw a circle. And this circle is my clock. And I would divide my 4 equal quadrants just like I would a clock. All right, minutes. But instead of minutes in here, this is representing my drip set. This is representing a 60 drop set. 60 being at the top and then breaking it into 4 equal quadrants. Now, once I have my problem figured out and I've concentrated it, or I've figured out my concentration per ml, remember, my problem is asking me for 5 mics per kilogram per minute on an 80 kilogram patient, and I have 400 milligrams in a 250 bag. I know that that's my desired dose, dose on hand, volume on hand, weight. 5 times 80 is 400. That becomes my new desired dose, and I concentrate this down. I divide that into that, but I need to convert my dose on hand milligrams to my desired dose micrograms, which gives me 400,000 over 250. Once I divide that, I get 1,600 mics per ml. This is my concentration. All right? Once I do that, once I concentrate my bag per ml, this number here goes on the top of my clock. All right? And then I just divide that into 4 equal quadrants as well. All right? 400, 800, 1,200, 1,600. I know I need to give 400 mics a minute. So I would give 15 drops a minute. Easy, huh? As long as it's in 4 equal quadrants, then this is mathematically sound. Now, there'd be some cases in dopamine where you would be estimating it. It'll be about 12, or it'll be about, that would be more like 6, or it'll be around 12. In that case, we don't want to do that for an exam. We want to write out the math problem and get an exact answer. But for problems like this, it's exact at 15. I'll give you another example of the clock method. All right. Now, we're going to go back to our lidocaine drip. Lidocaine is 1 to 4 milligrams a minute as my dose. If your problem says you want to give 2 milligrams a minute, what's your drip set? What's your drip rate? Well, this is perfect. So what I do is I try to concentrate a bag that's 4 to 1. How do I do that? Well, I know I have 250 ml bags, so if I put 1 gram or 1,000 milligrams into that bag, 250 divided by 1,000, 1,000 divided by 250, will give you 4 milligrams per ml. So I can go right back to my clock. 60 at the top, 15, 30, 45, and then, I should write that in the middle of this clock. But regardless, I got 4, 1, 2, and 3. All right? So if I wanted to give 2 milligrams a minute, I already know my drip rate would be 30. If I wanted to bump my lidocaine drip up to 3 milligrams a minute, I give 45. If I wanted to max out my lidocaine drip at 4 milligrams a minute, my drip rate would be 60. It's that simple. It is that simple. All right? And that's the clock method. Now let's do the same problem using our master formula. Desired dose times weight times solution set all over. Concentration and time. All right? If I want to give 2 milligrams a minute of lidocaine, I have 1 gram in a 250 ml bag. What's my drip rate? Well, my desired dose, we already know, is 2 milligrams per minute. I don't need weight. I don't need a solution set. Or I do. I'm sorry. I do. That would be 60. My concentration, remember, I got to take my dose on hand, convert it to my desired dose, which would be 1,000 milligrams in 250. That gives me 4 to 1. That's my new concentration, 4 to 1. And I don't need time, or 1. 2 times 60 here would give me 120. I got to divide that by 4 equals 30. That's exactly what I got on the clock. All right. So remember that. So now we're going to do some practice problems. All right. Well, let's look at this one. Read what it says. Your patient from above is we don't need to know all that. What we do, must start a lidocaine drip at 3 milligrams a minute. All right. Using a micro tubing set, which would be your 60 drop set. How many mLs per hour are necessary to satisfy this order, and how many drops per minute are necessary if the pump fails? Well, let's figure out what the problem's asking for, okay? We need to give a lidocaine drip, and that's all it's telling you at 3 milligrams a minute. So it's asking you to drip in. There's a problem right there. It's asking you to drip in lidocaine and for you to mix your own bag. So when mixing lidocaine, just go ahead and mix a bag that'll equal 4 to 1. How do we do that? Well, look at what size bags you have. Let's say you have a 500 ml bag. How many ml or how many milligrams would you put in that bag to make it 4 to 1? What about 2 grams? All right. We know we got to give it in milligrams, so we got to convert that to 2,000 milligrams over 500, which equals a 4 to 1 concentration. Let's go back to my clock. All right. 60, 30, 15, 45. On the top of my clock goes this top number. 4, 1, 2, 3. I want to give 3 milligrams a minute. My drip rate is 45 drops per minute. That's the clock method. Let's do this again using our formula. All right. So my formula is going to be desired dose times weight times solution set over concentration and time. Well, my desired dose would be 3 milligrams a minute. I don't need weight. My solution set is a 60 drop set because it's asking for micro tubing. My concentration, well, I mixed 2 grams in a 500 bag, which gave me concentration of 4 milligrams to 1 ml. So there goes 4 over 1. And then our time would be every minute, or we don't need it. Kind of is a moot point. So 3 times 60 is 180. All right, milligram a minute. Over 4 milligrams a minute. All right. And we also have drops up there because we still have this drop unit right there. So 18 divided by 4, or 180 divided by 4. So that goes in there 4 times, 16, 2, 0. That goes in there 5. The milligrams cancel out. The minutes cancel out. And my answer now is 45 drops. Pretty cool stuff, huh? That clock method works on a lot of problems like this. All right. All right, let's look at the next problem here. You have a patient who is presenting with an exacerbation of CHF. After the administration of nitroglycerin, you decide to give the patient Lasix at a dose that is twice that of his daily dose. The patient normally takes 40 milligrams of Lasix daily, so that's what he normally takes, 40 milligrams. How many milligrams do you give the patient? How many mLs will you drop from the vial? Well, the problem asks you to give a dose that is twice the daily dose, so if his daily dose is 40, all you got to do is times that by 2, and you get 80 milligrams. So that's how much you're going to give the patient. So that becomes your desired dose. So we know we got to give 80. Let's put this down a little bit more. Let's raise that up. All right. So we got to give 80 milligrams. We see from here that this Lasix is packaged 10 milligrams per ml. It's got 100 milligrams in 10 mLs. All right. So using our formula, again, I'm gonna write it down because we gotta memorize that. Desired dose times weight times solution set over concentration and time. Well, our desired dose, we already know, would be 80 milligrams times our weight. Well, we don't need weight because it's not weight-based, and we don't need a solution set, all right? Because it's not a drip, so we can cancel those two out. Our concentration is 10 milligrams per ml, and we don't need time. So which leaves us for a basic math problem. 10, or 80 divided by 10, which would be what? 8. My milligrams cancel out, which leaves me with milliliters. 8 milliliters. That's how much I would give. So I need to give 8 milliliters to give 80 milligrams. Pretty simple stuff, huh? Yep. Well, let's see what this problem says here. Let me erase that. You're treating a patient who has a possible broken hip and you want to give some pain management. You decide that the best course of action would be to deliver 75 mcg, micrograms of fentanyl. How many milliliters will you deliver? So the problem is asking you for milliliters. Well, let's see what we got here. We got 100 micrograms of fentanyl in 2 mLs. That's how it comes packaged. We got 100 mics in 2 mLs. Well, my dose on hand is equal to the units of my desired dose. So there's no conversion needed. But it's in 2 mL. So I need to divide 2 into 100, which would give me 50 mics per every ml. Now, you can kind of common sense your way through that one, but let's use the formula again to get this down. All right, solution set over concentration and time. So my desired dose would be 75. I don't need weight, so we don't need that. I don't need a solution set, so I don't need that. My concentration is 50 mics per ml. And we don't need time either. We'll put mics up there. So now it's just a simple case of dividing. Well, we know 50 goes into 75 one time. All right, so we got to get a decimal there, decimal here, drop to 0. 50 goes into 250 5 times. So that is now my answer. 1.5 mLs of fentanyl to give 75 mics. All right, you getting the pattern here? Pretty cool stuff. We'll do one more, then we're going to call this a day. Another bolus. Your patient from the above is not tolerating the situation, so you need to give her some Versed. All right. I need to give 2 milligrams of Versed. I have a vial here that has 5 milligrams in 5 mLs. All right. How many mLs do you draw up? So it's asking you for milliliters. That's what we need to find out. All right. So then we got to find out our concentration. So we have 1 milligram per 1 milliliter. So common sense would tell you that in order to give 2 milligrams, you need to give 2 mLs. Well, we're going to use our formula again. Weight, solution set, concentration, and time. And our desired dose is 2 milligrams. We don't need weight. We don't need our solution set. Our concentration would be 1 milligram per 1 ml equals, we don't need time. So 2 divided by 1, of course, is 2. My units of milligrams cross out, which leaves me with milliliters. So I need to give 2 milliliters to give 2 milligrams. Pretty easy stuff, huh?